We've had an introduction to Ampere's law, and we know how to calculate the magnetic field due to a single wire. So now we're going to look at some other things just a little bit qualitatively. So this is what I would like to do. Let's take a look at a wire here with its current, let's say this will be coming towards you, and another wire here with its current going away from you. And let's do this. Okay. All right, so let's see if we can't figure out what the magnetic field would be in between these two wires. Now, the magnetic field in between these two wires, and you guys have seen this in many circumstances, but just once again, a reminder, we have a linear system here. These are linear equations. There's no squareds or logarithms or whatever. So these are linear systems, which means that we can take the total of the field due to two of these is just equal to the sum of each of them individually. So what we're going to try to do is we're going to go ahead and try to find out the magnetic field right here at some arbitrary location R. Okay, so let's just qualitatively take a look. Here, this current is coming towards you. So once again, what do we expect from the right-hand rule? We expect that magnetic field to curve down. So this, let's call this wire 1, so it has a current of I1. And let's go ahead and call this one I2. So the current from B1 we expect to be like this. Excuse me. So what about B2? Well, now we're talking about current that's going away from you, and so now we would, sorry, it's backwards for me. Okay, so that means that our thumb goes in that direction, our fingers curl in this direction, and so we actually expect B2 to also be in this direction. So we expect both B1 and B2 to be pointing down, which means we're going to have a larger magnetic field here than we would if we just had one of those wires. Yeah, let's just leave it at that. Okay, but now what's the magnitude? Well, this is actually pretty darn easy. Let's go ahead and call this distance here D. Okay. So, what is the magnetic field due to one wire? Well, we already figured that out. So, from B1, it's just equal to mu 0 I1 over 2 pi r. Yeah, let's just go ahead and leave it at r since I've already labeled it that. So, 2 pi r, and r right now is just this distance from here to here. All right, well, what's B2? Well, look over here. It's going to be exactly the same thing. It's going to be mu 0 I2 over 2 pi r, mu 0 I2 over 2 pi r. But now, what is that r? How far is it from here to here? Well, if this r was 0, this distance would be d, and so what's this distance here? It's just d minus r. So here we have d minus r. And so, what's the sum? What's the total? The total will be, oh, I'm sorry, as long as we're here, and as long as we've done this qualitatively, let's go ahead and finish. If this is x and this is y, then what direction will this be? This will be in the minus j hat direction, and so will this, minus j hat direction. Okay, so that's just to get the complete vector expression for this. So our B total is going to be equal to mu 0 over 2 pi I1, yeah, okay, I'll do this in 2 steps. Sorry, I was going to do it in 1, but I1 R plus mu 0, yeah, okay, I'm going to cheat. We'll do this in more compact form. I2 over 2 pi d minus r. Okay, so if we, sorry, not quite right. This is a minus sign and j hat. Okay, so now all I've done is add these two things together, right? I pulled out the mu 0 over 2 pi in front, and now all we have is these two things here right now. One of these, this is B1, this is B2. All right, So let's make an assumption right now. Let's assume that I1 equals I2, and we'll just call it I. So I'm going to pull that I out from right here, and we can get rid of those. These are just 1 over. And then all we have is 1 over each of those, and we just need to do, oops, there's no 2 pi here. Sorry, I double counted that 2 pi. Okay, so this equals minus mu 0 I over 2 pi, and we have a d minus r, excuse me, that's d minus r plus r, and I'm just getting a common denominator here, r d minus r. Okay, and this is in the j hat direction. All right, so I'm going to, now let's just take a look at what we have here. And actually, what I'm going to do, I'm going to just once again, I'm going to cheat a little bit because I'm going to leave a little bit for you guys to do. So this, we'll just call this done, okay? So what do we have here? We have some constant, because I is a constant, times this stuff right here. I'm just going to draw you guys what this looks like, and I would like you to convince yourself that this is true. So this looks something, yeah, let's just go with this. This looks, I'll draw that on the same scale from 0 to d here. So now this is just the magnitude of b, and this is d. Okay, or this is still r. So this dimension is still our x coordinate, and this is now the magnitude of the magnetic field. And what we end up with is we end up with something that more or less looks like that. And like I said, you guys can convince yourself of that. You can work that out mathematically. So what you see is that as soon as we get away from the proximity of these two wires, we actually end up with a magnetic field strength that doesn't change too much. And it makes sense when you think about that, because as you get closer over here, this magnetic field is getting weaker, but this one is getting stronger, and they're both in the same direction, so the weakness of one kind of compensates for the strength of another. So qualitatively, that makes sense. Okay, now, I want to add to this qualitative discussion with just one more thing. So, now what we're going to do is I'm going to look at this exact same situation, except I'm going to look at it from the top. So, what I mean by that is this. What did we have? We had one wire where the current is going this direction, one wire where the current is going in this direction, and what we found was that between these we had a magnetic field that the magnetic field strength kind of went like that. All right. Now, however, I want to modify this a little bit. What if we also took another pair of wires and had one of them going in this direction, I, and one of them going in this direction, I. So, what's going to happen? Well, this is the exact same thing, right? It just rotated by 90 degrees. So, what are we going to have? We're going to have this exact same magnetic field strength in this dimension. So now what we would end up with is something where if we were to look at the magnetic field strength created by these four wires, it would be something like this, where it would be somewhat uniform in this region like this. All right, well, let's go ahead now. What would happen if we add this wire in and we add this wire in? Now we've just rotated by 45 degrees. So now we have a magnetic field strength that kind of looks like that. And what if we added another one in? That was this way and this way. And now we have another one. Well, if you can see that what you do is you get this region in here that is a more or less uniform magnetic field. But what happens is you keep adding more and more. For every one you add in that direction, you add another one in this direction. Keep adding, adding, adding. What do you end up with? What shape do you end up with? You essentially end up with a circle. So now we have a circular loop of current, and what do we expect that magnetic field to look like? We expect that magnetic field to be almost uniform all the way inside here. And it just makes sense going piece by piece. Now that we did this qualitatively, we are now prepared to look at it quantitatively a little more, which we will do in another video a little later. Okay,